All right, hey everyone. Just gonna wait for some people to get in and also set some things up. Foyez and Mike, is there anyone else I should be promoting to panelists?
No. Let's see if Kobe's able to join.
Michael, wait. Can you try speaking one more time? I can't hear you.
Let's see if Kobe's able to join.
Foyez, can you hear him?
I can hear him. Yeah, wait. Can you hear us? Yeah, okay, Akash. Can you hear me? Okay, I know Kobe is here, so we have to up.
Okay, I'll promote him.
Hi, Kobe.
Hey.
You guys will get started soon. So I'm pretty sure everyone is muted here, so that's what I see in the chat mostly. So this is a webinar, so you'll only be able to see us, but if you have any questions or comments during like any time in the presentation or the lecture, just type it in the Q&A chat, and we'll have people sort through it, and we'll get to your questions as soon as possible.
Yeah, so I see that we've had a lot of people join already. Just to answer a few of these questions, for all of you who are in the chat, you guys are all muted with camera off, so you don't have to worry. As Foyez said, this is a webinar, so only the three of us are being shown right now, so no need to worry about that. All right, yeah, so without further ado, let's get started. So hi everyone, we're so excited to start TrinMathCamp. We were so happy to see that many of you wanted to continue discussing our problems after you took TrinMath Virtual a few weeks ago. And we're so excited to provide this opportunity for all of you. So just to get started, we'll do some intros, then we'll do some pretty fun polls, and then we can get into the actual math. So I'm Michael. I'm a rising senior at Trinity, of course. I'd say that besides math, my main interests are debate and journalism. And I would say that my favorite part about math is the community, especially that we see at the competitions.
Hi everyone, I'm Foyez. I'm also a rising senior at Trinity. And so aside from math, I would say I'm really interested, I would say, in like chemistry, physics, and biomedicine. I really enjoy doing research in those fields. I'm just learning a lot about it, and I would say my favorite part about mathematics would be just like, problem solving with just like all our friends. Like we usually, the three of us and Maia, who isn't able to join us as right now. But I really enjoy just like solving problems with them. Just like, I think it's a really great community that we have.
Yeah, thanks. Hey everyone, I'm Akash. So obviously we all love math. Within math, I guess I'd say my favorite area is number theory. That's what I like to spend the most time on. Outside of math, I really like computer science, and I also play a lot of chess. All right, so we also, other than us three, we also have two volunteers who are going to be helping out with the Q&A today. So we have Kobe Brown as well as Francis. We want to thank them for spending some time with us and helping us out with this camp. And then if I'm not missing anything, I think we can get started.
Yeah, why don't we give a second? I believe our fourth captain is about to join.
Sure.
Before she's able to join, if you guys just want to quickly in the chat say where you're from, I guess. Akash, can you promote Maia to?
Oh, Maia? Yeah. I can start the polls also if you want. the beginning ones.
Okay, I see we have some people from Pennsylvania, New Jersey. Okay. Oh, England. Okay. Oh, very cool. We have people from all over the place. Hi, Maya. So we all just did an introduction. So if you just want to give a brief introduction, that'd be great.
Yeah, hi, I'm Maya. I'm an incoming junior at Trinity School, which is 11th grade. I'm really into like encouraging other people to join math. I'm the founder of Girls X Math and Girls X Math Camp, which are both mentorship programs for lower school girls at my school, and we meet every week. We have a lot of food to get them to like math. And yeah, I'm really passionate about sharing my love of math with others.
Great. So without further ado, let's get started with the polls. Akash, if you want to use the first few.
All right, so you should be seeing a poll now. There are just a few introductory questions, some serious, some, as you can tell, not so serious. So yeah, feel free to select some of those.
Favorite kitchen appliance. Oh wow.
That's my favorite question. But yeah, we're not going to use this information for anything. It's obviously just like icebreakers.
Yeah, it's anonymous as well. So
Someone said the submit button is not working.
the submit button is not working. We're getting some opinionated chats right now. All right, we'll just say a little bit more. Around over half of you have voted so far.
Six was hard decision.
Yeah, I saw that too.
It seems a few people are having issues submitting the poll. We're not exactly sure why, but we'll try to get to that. But no worries. You know, the polls are just for fun. Hopefully you'll be able to view all the presentations and whatnot.
All right, so I think let's share the results now. All right, so we have a lot of East Coast today, a fair amount of Canada, some West Coast, some Asia and Europe. That's got to hand it to you guys for dealing with the time zones.
Vanilla.
The ice cream flavor, vanilla. Yeah, I'm not sure about that. I gotta go with chocolate or something weird, like something interesting from like Ben and Jerry's.
Did we put math as one of the ice cream flavors?
We did, and a whopping 26% of people said math is their favorite ice cream flavor. So yeah, I guess if I don't go with chocolate or Ben and Jerry's, I'll go with math ice cream.
You missed out on cookies and cream there. There's none of that.
That's true.
Oof, I would go with cookies and cream. All right, there's also favorite TV show, Avatar: Last Airbender. All right, Michael, you have some people here. Office, Friends, classics. SpongeBob, that's, oh wow, SpongeBob was our winner. That's nice. Favorite kitchen appliance, chopsticks. Chopsticks are nifty. Yes. Nice. Favorite branch of math, algebra. That's cool. A lot of us are actually pretty interested in algebra, so there's a little bit of bias there in these presentations. especially tomorrow. We'll have a lot of algebra tomorrow. So for the 63% of you, definitely tune in tomorrow. You'll have a lot of fun. And, do you love math? The ultimate question. All 100% of you said yes.
Nice.
Which is amazing. So you're in the right place. All right. So unless there's anything else you guys want to say, I think I can start screen sharing the presentations.
Sure thing, yeah.
All right, let's see if this works. Okay. All right.
Can everyone see? Can everyone just type in the chat to make sure that they can see the presentation? Okay, great. It looks like the majority of you can see it.
I can't quite see the chat when I'm screen sharing. So is it all good?
Yep.
All good.
All right, great. So as you can tell by the title slide, today we're going to be talking about the pigeonhole principle. So whether you have no idea what that is or have already heard of it before, we're definitely going to start by going over at least what exactly does that mean, and then we're going to some problems about it. So even if you've heard about it, there'll be some interesting problems for you to think about. All right. So just before we get started, there are a few logistics. So we have 2 sessions each day. So some of you might know this just from the emails. We really want to make sure everyone understands. So we have 2 sessions each day. The session for grades 5 through 8 will be held from 3 to 5. So that'll be in around 2 hours. And anyone who's in this session right now, feel free to go to that one as well. The grade is by no means a restriction. And then, of course, the grades 8 through 12 is happening right now, and that'll always be from 1 to 3 this week.
Yeah, and I know a lot of you had asked or emailed us about that, if you're a rising 7th grader or 8th grader. So it's great if you guys are already here. If you think that the material today is, a little bit too difficult or a little bit too ahead of where you are, then feel free to join us at 3 p.m. For the grades 5 through 8 session. And I'm sure that might be a more appropriate fit for y'all. And to answer your question, I just saw that, yes, the recordings will be available on YouTube afterwards.
All right. Now just into the structure of how each day is going to work. So every day we're going to introduce some new concepts. So today it's the pigeonhole principle. And then we're going to try to, after going over these concepts, apply them to some fun problems. So that's typically how the structure will work. We'll have you thinking along the way in these sessions. And then there'll be a little bit of homework, which obviously there's no stress about it at all. We understand people have lots of things to do. So if you have some time, definitely look at the problems. Even if you don't have time to solve all of them, which sometimes the homework can be kind of long. So, that's definitely shouldn't try to do that. But I do think it definitely is helpful to even just look at them. I find that even when I don't have time to do homework, but I just spend time just staring at the problems for 5 minutes, just helps things seep in. And then lastly, the concepts we're going to cover. So today's pigeonhole, and then later in the week, we're going to cover some inequalities, some counting and probability, some complex numbers. So then there's also Mandelbrot sets, which has to do with complex numbers, and then game theory, which should be a pretty fun topic.
Yeah, and we're getting a lot of questions about homework. So, this presentation is just a bunch of problems to help you understand the concepts we're going to be teaching. And then towards the end, of course, if we don't have time for a lot of the problems, we're just going to allow you guys to do them as homework. And by no means is it mandatory. We're just giving to you all just for extra practice, and we're going to send out a feedback form afterwards. So if you have any questions about the homework, the material, or any comments about, our presentation or feedback, we'd love to hear it. And we'll be able to get back to you during the start of the next day. We'll be able to answer a lot of those questions.
All right. So before we begin with Pigeonhole, we just want to go over some mathematical notations. They're just some things that are fairly understandable, but just want to make sure everyone's on the same page. So first, we're going to deal with some different types of numbers. So natural numbers, typically you see them denoted by a fancy-looking n. And they're just the positive integers, meaning just things you would count on your finger. So 1, 2, 3, 4, and so on. The set of integers, typically denoted by z, is basically like the natural numbers, except it includes 0 and negatives as well. So this should be fairly intuitive. Rationals, so a little bit more complex. You can think of them as just fractions. So here we include the formal definition, which is useful when thinking about proofs and whatnot, but really you're just saying fractions. So for example, 3/4, 2/3, things like that. And then this might be a little bit of fancy language that some of you might not know. So coprime here. So what we're saying by coprime, in what we're really just saying here is that the fraction's in simplest form. So you don't want to have 2/4. You just want to have half. There's no, you don't want to think about fractions that are in complicated forms. You just want to simplify them as much as possible. So another way of saying this is P and Q don't share any common factors. So R is a set of real numbers. So the actual definition of these is fairly complex, but intuitively, it's really just the numbers you've dealt with throughout your life. So anything that you can find in a number line, that's a real number. All right, so the floor function. So the floor function, typically we denote it like this. So there's kind of some brackets on the side, but they only have the bottom. It's because it's the floor, floor is the bottom. And then it's the formal definition is that it's the greatest integer less than k. But I think a more intuitive way of thinking about it is that basically you just have some number and there's some fractional or decimal points going after it. Basically just chop that off. So the example here, the floor of 2.5, it's 2, and then there's that fractional part of half or 0.5. So then what the floor does is it just cuts that off. And then the ceiling function, it's basically just the opposite. So if you have a number and has a fractional part, then you basically just go to the next highest integer. So it's essentially like rounding up. So if from 2.5, you round up to 3. If there were 3.7, the ceiling of that is 4. And then exponentiation, I'm sure you're all familiar with this. That's just basically repeated multiplication. So if you have k to the nth power, you just multiply kn times. So 2 to the third is 2 times 2 times 2, which is 8. All right. So moving on to the pigeonhole principle. So this is what the pigeonhole principle says, or at least a version of it. So I'll just read it out. If we have n+1 pigeons and n holes, there will be some hole with at least 2 pigeons inside of it. So this may sound kind of formal, but if you really think about it, it just makes sense. So if you have n holes and you want to put the pigeons in those holes, obviously there are going to be 2 pigeons inside one of the holes, or maybe more, because you just have more pigeons than holes. That's really what it's just getting at. So we can prove this formally. Formally, this is called a proof by contradiction. But even if you're not quite sure what that is, you can just reason through this. So just to get through this theorem formally, we can first assume that each of the n holes, they're n holes, we say they all have at most 1 pigeon in them. So we're assuming the opposite of what we're trying to prove. We're saying that there should be at least 2 pigeons inside a hole. We're saying the opposite of that is that they at max have 1 per hole. So if each hole has a maximum of 1 pigeon, then that means that the total number of pigeons, the maximum number of pigeons we could have, is 1 plus 1 plus 1 n times, right? Because there are n holes, 1 pigeon per hole, so n pigeons should be our max. But that's a contradiction because we said we have n plus 1 pigeons here. So because we have a contradiction, this initial assumption that at most 1 pigeon is inside the hole must be false. So if this initial assumption is wrong, what I'm highlighting right now is wrong, then what we want it to be true, that there's some hole with at least 2 pigeons in it, must be true. So this is like a formal proof of this theorem, but it should make intuitive sense. So, you have, you have two pigeons, let's say 1 hole, they're gonna have to share that hole. Now, there are some other ways of stating the pigeonhole principle. That's kind of the simplest form, but this is a a more abstract way of saying it, and it's more generalized, so it'll help you with problems that get a little bit more difficult. So you have a sequence of n positive integers, and then you add them all up. So this is adding them all up here, and then you subtract n and add 1. And that's how many objects you have. So in the analogy of pigeons and holes, you can think of the objects as the pigeons and the boxes as the holes. So you're putting that many objects or pigeons into n boxes or holes. And then we're saying that the first box contains at least q sub 1 pigeons, the second box contains q2 pigeons, and so on. So again, we proceed by something called a proof by contradiction. So when we do proof by contradiction, we just assume the opposite and then try to find something that doesn't make sense, some sort of contradiction. So if we assume the opposite, that means that every box has at most qi minus 1 objects. We said first box has q1 objects, so now we're saying at most q1 minus 1. The second box, we hope to find q2 objects, so now we change that to q2 minus 1. So we kind of just go 1 lower. And then now our goal is to try to find some sort of statement that doesn't make sense. So along this train of logic and thought, we're trying to find something that's wrong. So similarly, it's actually quite similar to the proof that we just did. So you consider, now that you've put this restraint on your holes or boxes in this case, you want to find what is the maximum number of objects, or in other words, pigeons you can have. So the maximum number, as we said here, is qi minus 1. So we just plug that in, and we get q1 minus 1, q2 minus 1, all the way up till qn minus 1. We just add them up. And then what you get is the sum of the q's minus n. This minus n comes from the fact that we have minus 1 n times. So minus 1, minus 1, minus 1 n times is minus n. However, this is a contradiction once again, because it is less than the number of objects that we had. We said that we had q1 up till qn minus n plus 1 objects. However, this doesn't have the plus 1, so we're 1 short. So that's our contradiction, so this must be true. And again, just describing some vocab, you'll notice that it says corollary here. So that's kind of a term used in math a lot. So really what that just means is that it kind of follows for something we did previously. So we previously talked about a version of the pigeonhole, and this one being so similar, we can call it corollary because it follows from that. So now we have another corollary, and this will be sort of near the end of some of the abstract stuff we do. So if we have p pigeons and h holes, then some hole contains the ceiling of p over h pigeons. So this is a more strong definition. We've first started with just n and n plus 1, and this is just more general. So we're trying to build up a more strong definition of pigeonhole, and then from there we can apply this to some problems. So I'll definitely note that this proof is more complex than the other two. And generally speaking, while the proofs are definitely great to understand, we do want to stress that it is more important really that you focus on the problems, I think. So this proof might be a little complex, but I'll walk us through it. So we're trying to place the pigeons in the hole so that we don't have the ceiling of p over h in any one hole. So again, this is that same kind of idea from before, where we're trying to assume the opposite and then end up getting to something that's wrong. So we're going to go about this process in an attempt to not find this hole, but then we'll show no matter what, we end up having that hole. So there's this thing called division algorithm. Basically, it's a way of rewriting a number. So so you can write p as hq plus r. So basically you can take q, multiply it a bunch of times, by a bunch of times I mean h, and then there's going to be some remainder left over, at least in the case that you know, p is on a multiple of q. So that remainder is r. So there's a reason why it's called q and r. This is quotient and remainder. So this is really, you can think of it as like division almost. That's why it's called a division algorithm. So this is the remainder, this is the quotient. And then because it's a remainder, it has this inequality property. And then you should observe that Q, so this quotient here, is equal to the floor of P over H. So Q really just means how many times does Q go into P? So for example, how many times does 3 go into 10? So you have 3, 6, then 9. So it goes in 3 times. And then you can also notice that 10 divided by 3 is 3 1/3. Take the floor, you get 3. And that's what we wanted. So this is just P over H, so you do the division to get your quotient. And then the reason we take the floor is just so we deal with integers. So if you remember, the floor just chops off that fractional decimal part, and that's exactly what we're looking for. So that's why we use the floor here. So if r equals 0, then we actually know that the floor is equal to the ceiling. So this is because if you think about it, let's say we're essentially dealing with the floors and ceilings of integers. Because if this is the case, if r equals 0, then p is actually a multiple of q. So if we just, let's do a numerical example with multiples. So let's say you have 7 and 14. So if you take 14 divided by 7, that's p over h, you get 2. So the floor of 2 is just 2. It is no fractional part, so there's nothing to chop off. So you get 2. The ceiling of 2 is also 2, because there, again, is no fractional part, so you're just stuck at 2. So whenever you're dealing with integers, the floor and ceiling are exactly the same. So then here we're done. So we found our hole, that's the ceiling, because the floor essentially is the ceiling. Now, sorry for the typo, this should say r, but if r is greater than 0, if the remainder is greater than 0, then there's at least one hole with the floor of P over H plus 1 pigeons in it. And this is actually equal to the ceiling. So again, we can do a numerical example. So let's say you take 3.4. The floor of 3.4 is 3, and then you add 1 to get 4. And the ceiling of 3.4 would be 4. So whenever you have some sort of fractional part, taking the floor and adding 1 is the same thing as just taking the ceiling. So regardless of whether r is 0 or bigger than 0, we find our hole that has P over H pigeons. So now that we've gone to some of the theory of Pigeonhole principle, what it means, now we're going to work on some problems. So this first one, it's a little bit more straightforward, but it should get us used to dealing with the Pigeonhole principle. So I'll just read it out, and then maybe we can take some time to think to ourselves what the approach might be. So we have a school of 6 students, and then the school policy states that students can only wear blue, green, red, black, or white shirts. And you want to prove that every day there will be at least 2 students wearing the same color shirt. And of course, you have to assume that there's perfect attendance and people are adhering to this rule. But the goal here is just to show in this scenario, you're going to find, no matter what, 2 students who are wearing the same color shirt. So why don't we take a few minutes, we can think about it, and then we'll go over it.
Just to clarify, I saw some questions about the division algorithm, or rather corollary 2. And, you know, as Akash said, it's really just a more formal way of talking about how we initially introduced Pigeonhole. Really just saying, you know, if there are more, you know, items than possible holes, then of course each of the holes will have to have like multiple items. And what the division algorithm is really saying is, just by division, let's say you had 8 items that you're putting into 3 holes. You know, if you divide 8 by 3, you're getting 2 2/3. You take a floor of that, that's 3. So at least a few of the holes have to have 3 items, because, you know, just because, you know, as Akash said in the introduction, with the proof by contradiction, if we assume that the 3 holes all have 2 items, we're only going to be able to fit 6 items, right? We still need to put 2 items in, and wherever you put the 2 items, you'll see that the hole, at least one hole, has to have at least 3 items. So that's really just what the division algorithm is saying. The way that we put it on the slide is just a more mathematic or formal proof of it, but logically it follows from the same It's very, very similar to what we originally introduced in the proof by contradiction. So whichever way helps you better understand it, you should go by that. So can we just get a sense in the chat where people are with this problem? Oh gosh, someone is asking you to go back to slide 5 briefly. Yeah, also we had some questions about what a corollary was. So a corollary is just a statement that doesn't necessarily need too much proof, like because there's already some pre-existing theorem that supports it. So I know exactly for corollary 2, it was directly shown by the division algorithm, or we directly use the division algorithm to show that. So it seems like.
And just to add to Michael's explanation of the corollary, typically you'll kind of see things categorized by like theorem or stuff like that. So a corollary is almost in a way like a mini theorem. So it's just not so big that it grants to be called a theorem in whatever text you're dealing with, but it's worth mentioning, or thinking about, and is kind of along the same theme that you've been dealing with. So that's what a corollary is. So we were dealing with a pigeonhole principle before. This is kind of an extension of that, so that's why we called it a corollary. But again, that's just terminology, so don't stress too much about it. And I'm just going to flip back to problem 1, just in case people need to see it.
Yeah, so it seems most people are done with the problem. So, gosh, you just want to go over it briefly?
Yeah, sure. So this is straight up applying Pigeonhole. So we have 6 students. So you can think of, so you have 6 students and you have 5 different colored shirts. So therefore, there are going to be at least students wearing the same colored shirt. So this is kind of like the first statement, so I'll just flip back really quickly. So this is like if you have n+1 colored shirts, and then, sorry, you have n+1 students and then colored shirts, then there's going to be 2 people wearing the same colored shirt. So let me just, all right. So I'm just going to launch a poll. Give me a minute. All right, so you should be seeing a poll right now. So I'll just explain what I mean by these questions. So at least when beginning to think about pigeonhole principle, I think it's often useful to think about what are the pigeons and what are the holes, just drawing it back to that analogy that that we used. I mean, we by no means had to call this pigeons and holes. It just, that's what I guess mathematicians decided to do. But I think it's useful to see, you know, what's the pigeon, what's the hole, so we really know how we're applying this theorem. All right, so we see the votes coming in. All right. Almost done. Okay. So it looks like most of you have voted, and the vast majority of you got it right, but we'll explain anyway. So the pigeons are indeed the students, and you have the holes being the colors of the shirts. So if you kind of just replace the words with pigeon and hole, it actually makes a lot of sense. So if we just go to the solution here and we read, we have 6 pigeons as opposed to students. So we have 6 pigeons and 5 holes. Then there will be at least 2 pigeons wearing the same shirt is basically the same thing as in the same hole. So when we read it like that, it's actually really just the same thing as what we showed earlier on like slide 2 or 3. So yeah, the thing like over 80–90% of you got this, so that's great. So yeah, again, the pigeons here are the students, and the colors of the shirts are the holes. So we have more students than colors of shirts, so therefore we're going to get at least 2. All right, so let's move on to the next problem. So this is definitely more complicated. It is not just simply just, plugging in. You have to be a little bit smart about this. I'll just read out the problem. Prove that if we color a plane with the colors blue and red, there must be 2 points of the same color that are 1 unit apart. So we'll let you all think about it for a little bit. If you have any ideas, of course, feel free to put them in the chat. And otherwise, we'll give you guys a little bit of time. And we do have a hint ready, so maybe we can display that in a couple minutes or something, just so we get time to digest it. And then, of course, we'll reveal the solution.
Yes, just to answer your question, Alex, you do color the points.
Okay, so we're getting that some people are a little bit confused by the question, so maybe I'll just explain this a little bit more explicitly. So when we say color the plane, we basically just imagine, like if you ever did any graphing or something like that, just basically like a 2D plane. So you can think of it almost as the screen you're looking at right now, or a piece of paper, but just infinite, of course. And the idea is that for every single point on that plane, you're going to color it blue or red. So that entire plane will be have some color, and it'll either be blue or red. And the idea there is that in this infinite plane, we can find 2 points that are the same color, and their distance between them is a unit apart. So I hope that clears up what the question means. Someone said it reminds them of the 4-color theorem. That is definitely more complicated, but I can see why your head is directed there. Yeah, Michael had this suggestion in the chat of thinking of the plane as a coordinate graph. So that can be a helpful analogy. And if you're still confused by the question, of course, just put in the chat or Q&A or something. We'll try to address it. All right. So I think we'll drop the hint now. So the hint is to draw an equilateral triangle of length 1. So it doesn't really matter what equilateral triangle it is, where it's located in the plane, just draw one. And then think about what your pigeons could be, what your holes could be. And it's always useful to think about what is the end goal? What are you trying to prove here? What are you trying to show? All right, we'll give it maybe about a minute, maybe a little bit less, and then we'll start talking about how to approach this. So I think there's a suggestion here that kind of illuminates maybe something that people aren't quite understanding. So, so someone suggested to color it like a chessboard. So I just want to be clear that we're actually trying to show that this statement is true for no matter how we color it. So you can think of this like you give a piece of paper to your friend. Again, I know a piece of paper is finite, but the plane is infinite. But since infinity is a little bit weird to deal with in real life, let's just say you give your friend a piece of paper, give them a blue marker, a red marker, and they color it. Of course, imagine this is a scale, so it's infinity. And no matter what they give back to you, no matter what drawing they give to you, you want to be able to find the 2 points of color. So you actually can't choose how we color it. You really want to show that no matter what coloring we choose, we end up with this ability to find 2 points that are the same color and 1 unit apart. In the chat, also getting some nice solutions here.
Mm-hmm. Seems like a lot of people understand it. Perhaps, Akash, if you could annotate your screen. Oh, actually, I can annotate. Perhaps showing, if we just draw a quick triangle, a lot of people are already getting it. So just to clarify, right? Like, let's say we have 1 point on the plane right here, right? And then we have another point on the plane that's red over here. So if we complete this triangle, right, and this is with silence 1 by 1, let's just assume we don't know this. Let's just assume we don't know this the color of this point yet. Let's just say it's black, not red or blue for now. We don't know it. You can see that regardless of whether this black point is actually blue or red, ultimately you're going to have, oh, sorry. I should have done this way. Sorry, this point over here is going to be blue, right? So ultimately, regardless of whether this black point is red or blue, you'll see that we're going to have at least 2 points, or we're going to have 2 points that are a unit apart, right? Because you have, by Pigeonhole, you have 3 points and 2 colors. So at least 2 of those points are going to have the same color. And that's just Pigeonhole. I think Akash is going to release a poll soon just to check that you guys have an understanding of what's the pigeon here and what's the pole.
Yeah. And then just to put the formal solution down, so yeah, thanks, Mike, for the visualization. All right, great. So yeah, so the idea, you draw the triangle with side length 1. You have 3 vertices, but you only have 2 colors. So then you're going to find 2 of the colors, which will have the same color, which, as Michael said before. So I'm just going to release a poll right now. Again, similar to the last one, we're just going to think about what are the pigeons in this scenario, and then what are the holes. So you should be seeing a poll right now. Same format as last time. So some of you are asking the question, why an equilateral triangle? So it's definitely a very great and natural question to ask. Whenever it's always, sometimes you can often improve things just by it seems, without logic almost, like where did that equilateral triangle come from? How does anyone think of just equilateral triangle? Why not a circle or a pentagon or something? So let's try to get some intuition for that. I think just because the poll is almost done, maybe we can cover that first really quickly, but we'll definitely give intuition for an equilateral triangle, because the goal here is not just to understand one problem, it's to really understand it completely so that you can apply it to other problems. All right, so it looks like most of you voted. So again, the vast majority of you have a great understanding of this. So yes, the pigeons in this scenario are the vertices, and the holes are the two different colors. So again, I think it's always a great way to just basically plug them in almost as synonyms into the sentences we write. So if we just read this differently, thus we have 3 pigeons and 2 holes. So 2 of the pigeons will be colored with the same color. So in our analogy, what that means is that 2 pigeons are in the same hole. So 3 pigeons, 2 holes, and then that's what we have. So just because I want to address the question I talked about earlier, why an equilateral triangle? So first, what's great about an equilateral triangle is that one, you have 3 objects. So the objects here are the vertices, or in other words, 3 pigeons. So you can kind of, if you first realize that the pigeonhole principle is what you need to use here, which is a little bit of a given since this is a pigeonhole principle presentation. But once you figure that out and you see that there are 2 points of the same color, it's very key that there are 2 points of the same color that need to be a unit apart. The fact that there are 2 probably is an indication that you're probably looking for 3 pigeons, because you always just want to be one above, right? If you remember back to that first definition we gave you, it's that you have n holes and n plus 1 pigeons. So you can think of the points of colors for holes, and you think to yourself, okay, how many pigeons do I need? You need 2 plus 1, which is 3 holes. So that's kind of why a triangle should come to mind, because you need 3 things. Now, an equilateral triangle of length 1, that's really using the 1 unit apart piece of information. So, you could draw isosceles triangles, scaling, but they're not quite going to be as useful, because what you really want are vertices that are a unit apart, so that you can relate your situation to the statement that you're actually trying to prove. So again, the triangle, 3 sides, 3 vertices, that comes from adding 1 to 2, and then equilateral of length 1, that comes from the fact that they're 1 unit apart. So that's a little bit of intuition as to how one might come to this solution. All right, so I think we can move on to problem 3. I think we're good on questions. So this is a classic problem. I remember this one. So if you have an n by n board filled with the numbers -1, 0, and 1, such that the sums along all rows, columns, and main 2 diagonals are all different for each other. So I'm just going to explain a little bit more of what this question means, just because some of the terminology might be a little bit confusing. So for an n by n board, I think maybe I should just draw like a 2 by 2 board or something, just so people get what we're saying. So if a 2 by 2 board would look something like this, again, sorry for the bad drawing. So this is what a 2 by 2 board is. It just means you have 1, 2 here, and then 1 and 2 there. So an n by n board would just extend n this way and then also n that way. So that's what we mean by an n by n board. And then each of those squares is filled with a -1, 0, and 1. And what we mean by rows, columns, and 2 main diagonals, sorry, maybe I should actually keep that drawing up. So I'll just draw a 3 by 3. I think it's a little bit more illustrative. All right, so the rows and columns, I'm sure you know what that means. So the sum of the rows, so this would be a sum here. So I don't know, if this were 1, 1, and 1, the sum would be 3. And then if this were like 0 and -1, then the sum of this column would be 0. What might be a little bit confusing is what we mean by main diagonals. So I'm just filling in this board randomly here. So main diagonals basically means the longest diagonal. So going from this corner of the board to the other corner of the board. So here, net 1 plus 1 plus -1 is +1. And then in the other direction, you actually have the same thing. So again, +1. So you have these two main diagonals, as well as your columns here and your rows here. So I just hope the visualization clears things up. We'll just give people a little bit of time to think about this. We have a hint ready, and then after that, we'll talk about the solution.
Yeah, and a good way to think about it, of course, is before we even release the poll, is what are the pigeons and what are the holes here? So thinking about, what are we trying to show must be different, right? And, what is the number of that? And then using that, perhaps you can really think about, I see a few people in the chat already, already got it. Really thinking about, what are we trying to show is greater than the holes? And then that's what we get for our pigeons. Yeah, gosh, I think you can show the hint. It seems like a lot of people are getting.
So I'm just going to delete the drawing so you can see the hint. So the hint, think about the number of possible sums. So for any n, how many possible sums are there? And how many rows, columns, and diagonals there are. So just think about how many options you have for those two things: the number of sums, and essentially like how many times you're going to compute the sum. So the rows, columns, and diagonals, main diagonals, that is. And also, I just want to add, this is an n by n board, so it's general for any positive integer n. But that said, it is a lot of the time very useful to think about just examples. So, dealing with a 2 by 2, a 3 by 3. So I know that some of you have already gotten a solution here, but even for this problem, or when problems get much harder, a very useful strategy is just to plug in smaller numbers to gain intuition as to how these cases work. All right, so we're getting some more solutions in the chat. Okay, some people have solutions for 2 by 2s and 3 by 3s, which is nice.
Right. Okay. So it seems like most people are getting it. So I'll just reiterate what a lot of people are already saying. So really, what we're trying to show here, as the hint says, is how many possible sums there are, and then how many rows, columns, and diagonals there are. So just starting off with the second one, since I believe that's a little bit easier to see. If we were to just draw, a sample n by n. This is just a 2 by 2, but let's just say this is n by n. The number of rows is obviously n, right? So let me just type that. So we have that rows equals n, columns is also n, and then if it's just a 2 main diagonals, then there's just two main diagonals. So in total, the sum of those is 2n plus 2, right? And so if there are 2n plus 2 possible sums to account for, then we have to look at what the actual possible sums are, and then see if we can show that it's going to be less than 2n plus 2. So looking at the possible sums for any row, right? So any row has n items, and in an n by n board, if it can be filled by the numbers -1, 0, and 1, the bounds or the limits of that possible sum is going to be, the lowest is going to be if all the boxes are filled by -1, and the highest is going to be filled if all the boxes are filled by 1, right? So if they're all -1, then we see that, so if all -1, then that means that the sum of that row is going to be negative n, right? And if it's all 1, then we see that the sum of that row is going to be n. And so from negative n to n, that's all of the possible sums that we can get, right? It could be negative n plus 1, negative n plus 5, but ultimately it has to be bounded between negative n and n, like inclusive. And so if we take that bound, then clearly we'll see that this covers all the integers from negative n to negative 1, 0, and then 1 to n. And then we can see that from negative n to negative 1, that's n integers. 0 is its own integer. And then 1 to n is another n integers. And in total...
Hey, Mike, just a reminder, just make sure you press enter at some point because they can't quite see your screen. So just make sure you submit the text box.
Sure. So here's what I was just typing over here. So yeah, so we get that the possible sums is going to be 2n plus 1, right? It's going to be bounded from negative n to n inclusive. And if we only have access to 2n plus 1 sums, but we have 2n plus 2 to account for, then we can see that at least one of those sums has to be repeated with another sum. So if everyone understands that, Akash, you have anything to add to that?
Not really. I think you covered it. I can just display the solution we wrote up, but it's really exactly the same thing. Fine with you, I think. Can I delete the?
Yeah. Okay.
So it really is exactly as Michael said. So we just computed it in the other order. So the number of rows, columns in main diagonal, the possible sums is between negative n, and that's because, as Michael said, if you want to minimize everything, you take the smallest number you have, negative 1, you add that n times, you get negative n. Same logic for positive n, and the number of integers there are 2n plus 1, because you have 1 through n, negative 1 through negative n, and then the plus 1, you got to remember 0. Number of rows, columns, it's n plus 2, as Michael said. So then by the Pigeonhole principle, there are at least 2 rows, columns, or main diagonals that have the same sum. So Michael alluded to this earlier. We're going to do the same poll again. Should be quite familiar with this now. So we're just going to poll, what are the pigeons and what are the holes? All right, so there should be a poll going on right now. Again, so what I like to do is just plug in synonyms into the proof that we wrote. I think that often gives a lot of insight. This one's definitely a trickier example, so no worries. All right, over 75% of you voted, and it's going up, so I think we can discuss it now. So yeah, the majority of you got it right. This is definitely more tricky, however. Yes, the pigeons are the rows, columns, and main diagonals. So you have, and then that would leave the holes to be the possible sums. So I've been talking about synonyms, but I think another way which could be useful to think about it is that if you have 2n plus 2 pigeons and 2n plus 1 holes, then there's going to be some pigeon, 2 pigeons sharing the same hole. If we just put it back in there, if you say that there are the number of holes is, the number of pigeons is 2n plus 2, then it all makes sense if we go back to the original definition of n and n plus 1. All right. So it is 2. It's been around an hour since we started. There's another hour to go, but we just wanted to give you guys a quick break. So in around 5 to 10 minutes, if you guys could please come back. That's when we're going to start up again. It's hard to sit down for just 2 hours straight, so we're going to give you guys a little bit of a break. So we'll be back at around, so it's 2 p.m. Eastern time. So we'll be back most likely close to 2:10. And I'll just leave up the next problem if anyone wants to think about it. But go on a break, do whatever you need to do, and we'll be starting up soon.
Hey everyone, so I think we're gonna get restarted. So, um, okay, so can you guys see the screen? Just make sure. Okay, great, and let's just make sure everyone is back. Okay, great. So I assume that perhaps some of you have been thinking about this problem like during the break. And so just like I'll provide just like a hint on what to do next, just to see like essentially like how you would approach this problem. So perhaps some of you can think about splitting the unit square into 4 equal subsquares. And so I'll give you just a couple of minutes to think about that.
Yeah, also just to add to what Foyez said, I think what we've been doing previously also might be useful. So again, just thinking about what are the pigeons here, and then what are the holes, I think is a good way to think about how we can apply the theorem.
Okay, great. So let's actually just go into the solution right now. So after we divide the unit square into 4 subsquares, you can notice that by pigeonhole, since we're placing 5 points into this square, there will be at least 2 dots in the same subsquare. And so you can notice that the longest distance in each subsquare is square root of 2 over 2, which is essentially just the diagonal of each of these subsquares. And you can verify that for yourself. And so that essentially proves the claim. Does anyone have any questions?
Yeah. Also, I think so. Earlier, when we were talking about the equilateral triangle question, there was this great question on, how do we know to deal with an equilateral triangle? So then in that scenario, we said that we had 2 colors. So therefore, it made sense to do 2 plus 1 and equals 3, having something with 3 vertices, or in other words, 3 pigeons, so that we could get that pigeonhole principle in action. So in that scenario, we were essentially trying to construct something to create pigeons. And in this problem, we're constructing a shape to be the holes. So it says 5 points. So when you see 5 points, first off, it should be somewhat clear that the points aren't holes, right? You can't really put something in a point. In the other case, the points were the holes because you could color them. But here we're placing them on the plane. So you really place the points in a hole. So you have the pigeons, 5 pigeons, and you need to create the holes. So if you want to use the pigeonhole principle with 5 pigeons, it probably makes sense to have 4 holes. Because if you remember the first definition we gave you, you have n holes and n plus 1 pigeons. So that's kind of the intuition that should lead you to think to take what you're dealing with, which is a unit square, and divide it into 4 things. And you'll notice that it's often best to divide them into 4 equal things. Like we had an equilateral triangle, here we have 4 equal subsquares. It wouldn't really make sense to just divide it into 4 like, you know, nonsensical like regions of area. It's in the same vein that, you know, you wouldn't want to have like a scalene triangle with just all different side lengths. So 4, it kind of comes from the 5. So you subtract 1 to get 4 because you need 4 holes. And then from there, you have to put those 5 points, and then, you know, 2 of them will be in the same subsquare. And then from there, it all follows. But I just wanted to key in on that intuition for the 4 subsquares. It really comes from the fact you acknowledge that the 5 points are the 5 pigeons. You need 4 holes, so you got to have 4 subsquares. Anyway, Foyez, back to you.
Yeah, and I see that a popular question is like, so what if we place the points like exactly in the middle or on one of the edges? So I assume most of you can see my cursor, right? The little hand. So so if you place it on like some edge like this, like right here in between these two subsquares, you can consider it in some sense as like a part of both squares. So I think that would be the best way to do it. And like you can choose whichever is convenient for you. So essentially like the worst case scenario would be like if our distribution was like there was 1, 1, 1, 1, a point in each of the subsquares, and then some point lies on this line. But I can also just consider that as a point in either square, whichever one suits my needs best. And someone asked if we can place it in the exact middle. So if we place it here, in some sense, you can also like consider that as that point as an element, as basically an element of any of those subsquares, right? Because this middle point is part of like each subsquare, and so whichever one is convenient for us to show that there's only root 2 over 2 unit, that 2 points are at most root 2 over 2 units apart, we'll use it just for that square. But it works through the exact same logic, because our whole reasoning was that the longest distance in a subsquare is root 2 over 2, and that's essentially from any diagonal, right? And so even if a point is in the center, like the longest point will still be root 2 over 2. Yeah.
All right, so I think we can go to problem 5.
Let us do it. Okay, awesome. So problem 5 states that in a 10 by 10 square, there are 101 points such that no 3 of these points lie on a line. And we want to prove that some of 3 of these points form a triangle whose area does not exceed 1. So again, let's try and like remember, you know, try and figure out like, you know, what we want as our pigeons and what we want as our holes. And I think that'll help a lot of you just figure out the solution.
Yeah, and if any of you have any ideas while you're thinking about it, feel free to put them in the chat as always, and we'll try to respond. All right, Foyez, do you think we can drop the hint now? All right, so you'll note this is a similar theme in terms of taking what you have and then splitting it into smaller things. So again, I would advise thinking about the pigeons and the holes here. And this also requires a little bit of extra work because you're gonna need to think about what it means for 3 points of a triangle to have an area less than or equal to 1.
Yeah. So some
like
of
what
you
kind
also,
of configuration do you need to have?
yeah, so some of you also suggested in the chat to split it up into essentially 10 by 10 subsquares. And in essence, it's a very similar problem to the last one where we showed that you know, if we split into 10 by 10 subsquares, there will be like 2 points in one subsquare. But I think what a lot of you should consider is that we're trying to form a triangle which has 3 points, and not and 2 points really doesn't help us too much.
So we're getting a lot of great ideas and solutions in the chat and Q&A. So I think Foyez will lead the solution for this problem now.
Yeah. So if we took our hint of splitting the square into 50 2x1 subrectangles, then by the pigeonhole principle, we can say that there will be at least one subrectangle with 3 points in it. And now you have to notice that the maximum area of a triangle that's contained in a subrectangle is 1. And so we first have to understand why this is the case. So we understand that the area of a triangle is given by base times height divided by 2, right? And so when we take a subrectangle that's whose dimensions are 2x1, the largest triangle we're going to be able to fit in there is just half the area of that subrectangle. And that's because the longest base we can have and the longest height we can have is 2 and 1 respectively. And so that's kind of the idea behind it. And so that essentially shows that that there will always be 3 points that form a triangle whose area does not exceed 1. And I think based on a lot of your comments in the chat, a common misconception some of you are making is about what Pigeonhole tells us about the distribution of points. Pigeonhole only tells us about, essentially you can think about it in terms of kind of the worst case distribution. So this tells us that there's going to at least, the Pigeonhole principle that we used here tells us that there's going to be a subrectangle with at least, there's going to be at least one subrectangle with at least 3 points. But there could very much well be 100, all 101 points can be in one subrectangle. And so it definitely doesn't tell us anything about it doesn't tell us about too much about the distribution, but it tells us at least, the worst case scenario, the minimum information that we have is that there's going to be at least 3 points in one subrectangle.
Yeah. So, and again, I just want to add to that. I think we've been talking about sort of how one even begins to think of these solutions. It's kind of almost two different things to, one, see the solution and then get why it works. But I think what's really important is to understand how whoever wrote the solution got there, and so that you can replicate it for similar problems. So I think, a suggestion that we were getting a lot is to think of the 10 by 10 square as 100 1x1 unit squares, which is a very logical direction to go in, considering what we've done in the past. We've had a lot of, breaking down, for example, that unit square into 4 smaller subsquares. And it makes a lot of sense because we have 101 points, you split it into 100 sections, so there's going to be 2 in the same square, which is great, and that definitely is an application of Pigeonhole. But you also want to think about what are you really trying to do here. So it's not just that 2 points have some sort of distance, but now you're actually talking about 3 points because you're forming a triangle. So when you have 3 points, that's why we had this 50 2x1 rectangles. So someone in the chat actually used the, I believe the second corollary of the Pigeonhole principle that we talked about, which is you take the pigeons divided by the number of holes and then take the ceiling. So if you already have the pigeons, which are the 101 points, and you're essentially trying to create holes here, right? That's what these subrectangles are, they're holes. So if you note, 101 divided by 50 is 2 point stuff after it. And then when you take the ceiling of it, 2 and the fractional part gets to 3. And that's exactly what we want. So if we just had 101 over 100, that's 1.01. So the ceiling of that's 2, but we need 3. So getting down to 50 gives us that ceiling of 3 that we need. And then from there, it's a little bit of geometric logic that you have to reason that 3 points inside a 2x1 rectangle will form a triangle of less than half the area. So that's half of 2 is 1. So we get there. But yeah, just thinking about what your pigeons are and thinking about your holes is a good idea. And thinking about not just
and thinking about how many holes you need, I think is an important idea.
Yeah, just adding on to Akash, I think a big thing that he's talking about is also, with the misconception of of trying to split it into, 100 subsquares. A lot of you did note that there would be at least 2 points in a subsquare, but again, the way we get these clean proofs is by having, by usually using, corollary 2, which is taking the ceiling of the pigeons divided by the whole. And a big thing to understand is that we don't know. There's many cases of how we can distribute each of these 101 points, and it's very hard to make an argument is saying that after you split it into 100 subsquares, that if there's 2 points in one square, we don't really have much information about that third point, and it's very hard to argue. So when you have when you split it in, if you can cleverly figure out a way to split it into these 52 by 1 subrectangles, it'll just give you a much cleaner solution. So yeah, let's move on to the next question. So problem 6 asks that us to prove that if we draw 9 lines within a square such that each of these lines divides the square into 2 regions of area in ratio 2:3, then 3 of these lines will be concurrent. So again, just to reiterate, let's try and figure out where what we want our holes to be, and how can they give us essentially how can they give us our desired results. Oh, okay, so there are some questions in the Q&A about the definition of concurrent. So concurrent just means, so when we say, so suppose you take 2 lines, we say that they're concurrent if they intersect, and of course 2 lines that are not parallel will intersect at a point. But when 3 lines are concurrent, they essentially, all 3 of them intersect at the exact same point. So I hope that clarifies any questions. Okay, great. So let's go into the solution. So let's say we take a vertical line that divides the square into two regions of area 2 to 3. And this is just a line that I constructed, FE, right? And so we should notice that our vertical lines must go through point G. And that, in fact, that any point that essentially divides the square into regions of area with ratio 2 to 3 actually has to go through point G, which is the midpoint of FE. And so why is this the case? What you can notice here is that in line HI, we see that this triangular region is equal to this triangular region, right? And so we're essentially keeping the ratios of the area the same, because we're essentially, as we rotate the line around G, we're keeping the areas the same. We're essentially trading one piece of area for another piece of area, right? So suppose we take this as one of our areas, the area of quadrilateral HCDI, and we compare it to quadrilateral AIHB. We see that this area, the area of triangle IFG, is interchangeable for the area of GEH because these triangles are congruent, or in other words, they're basically the same, and so they have the same area, and so we're essentially just trading areas. So I hope that makes sense. And so, and then we have to notice that there's actually 4 of these types of points. So 4 of like our point G's. And so why is that the case? So we can construct a vertical line EF here. And then we can also construct one just shifted to the right, because we're not splitting our square into areas 1 to 1. We're actually splitting them into 2 to 3. So I can create one here that splits this side into 2 and this side into 3. As well as if I shift it over, I can create another line here. But I can also create 2 horizontal lines like that split it into 2 to 3. And you'll notice that if I take the midpoints of each of these 4 lines, our lines have to go through those points, just because, at least one of those points, just because of this whole idea of like trading areas that I talked about. And so this is where we invoke Pigeonhole. So since there are 4 types of our point G, we can notice that if we draw 9 lines by Pigeonhole principle, 3 of them must go through one of our desired points. And I believe Michael is drawing some new points. There's actually 4. And so this is essentially the idea. And so why does I'll elaborate a little bit on the Pigeonhole principle part. So if you remember the corollary 2, here essentially our poles are essentially our 4 points that we wish to go through. We have G prime, as Michael drew here. We'll call this G double prime and G triple prime down here. So you can kind of imagine these points. And so our holes are these 4 points, and our pitches are these 9 lines. So 9 divided by 4 is 2.25. And if we take the ceiling, then we get 3. And so that kind of just shows that 3 of our pigeons will be going through one of these 4 points that we had. Okay, let's see, any questions?
Yeah, so that's a good example of Pigeonhole here. I know someone was talking about generalization, and I think that's really cool. So, the explanation that Foyez gave us about how these triangles are really just, you're kind of trading one triangle for another triangle of equal area. So if we see with any ratio, really, if we can just draw those vertical lines and horizontal lines, there's going to be 4 of them, unless, of course, the ratio is 1 to 1. But for any other ratio that isn't 1 to 1, if you draw those lines, regardless of where the ratio of what the ratio is, you can still draw like the slanted lines where the triangles are still going to be doing the same thing, where the area is going to be the same. And so it really works for any ratio. 2 to 3 was just an easier example just to just demonstrate this. But yeah, I think it's really cool that you can generalize this for any non-1-to-1 ratio.
Right. And just adding on to Michael, if you notice that like someone brought up the point of if we essentially split it into 1-to-1, and the whole idea of when we split it into 1-to-1 is that our point of symmetry will just be the center of this square, and that every point that divides it into a 1-to-1 ratio is going to be a point that goes through the center. And so you can realize that every single point will go through that center point. And so for if it was a 1-to-1 ratio, we could say that in fact all 9 lines go through the desired go through that center point. And so I think I've seen that a couple people are thinking about how do we divide the square into certain subsquares. So here I think since we don't really want to deal with subsquares, and so why is that? Well, you can see that when we have line HI, it doesn't necessarily, you won't be able to nicely fit any squares into that region. And so we always have to think about, what's going to be our most, what do we want as our holes and what do we want as our pigeons, of course. And so our pigeons, from the problem you can think about, of course, is our 9 lines. But constructing our 4 holes is really the more difficult aspect of this problem. And so essentially what we want to think about is, since there's actually, like we've shown here, there's actually like an infinite number of lines that split, that divide the square into 2 regions of 2 to 3, of area 2 to 3, because I can just rotate, I can continue rotating HI around G, and I'll have an infinite number of those lines. And of course, the other lines that go through the other 4 points also exist. And so that's the whole idea of that. And that's kind of why, instead of dividing the square into essentially, a couple subsquares, it's definitely better to think about, how can we construct a point? How can we construct 4 points that'll serve as our holes, and then we can apply Pigeonhole to it. And that's exactly what we did here. So I hope that's clear to everybody.
Yeah, sure. This is definitely like a tougher problem, but as Foyez was talking about, one of the more obvious ways of drawing one of these lines that divides the square into regions of 2 to 3 is, of course, a vertical or horizontal line. So maybe, my strategy might have been, let's draw one of those lines, and then let's see, what happens when I try to draw a line that isn't just a perfectly vertical or perfectly horizontal. And I think, once you draw one of those lines, right, like here we have IH, once you draw that line, then perhaps you can see that triangles IFG and GEH are always going to be congruent. And then all of a sudden, you might realize that G is a fixed point for any of those lines, right? So, this problem is a harder example of how we might use Pigeonhole, but you can see that Pigeonhole actually offers a very, clean solution to it. That really helps us, prove this problem.
I think something Michael was talking about that's important in math is just, pattern recognition. Like, if you don't know where to start, like when I first saw this problem, I definitely didn't know, like, the exact solution. But like, as soon as you start drawing and working through examples, usually when you work through certain cases, it really opens up the solution, and that's essentially how we come to these solutions. So with that being said, let's move on to the next question. So problem 7 says 41 rooks are placed on a 10 by 10 chessboard. Prove that there are 5 rooks who do not attack each other. So for those of you who don't play chess, I thought I would explain this a little bit. So essentially, when we have a 10 by 10 chessboard, we're essentially we have a 10 by 10 grid with 100 squares in it, and we place a piece in each of these squares. And what a rook does is a rook can move horizontally and vertically. And so essentially we're trying to show that wherever we place these 41 rooks, we'll always be able to identify 5 rooks that don't attack each other. Meaning that if I were to move them horizontally or vertically, I won't be able to essentially run into them or essentially take the other rook. So I hope this is clear.
Oh, and Foyez, can you? Oh, there we go. Maia's there. Yeah. So in the interest of time, maybe we're gonna just think about. Wait, Foyez, is there a hint for this problem, or can I just?
What?
Wait,
Let's give a couple more minutes. I think I believe this will be our last problem.
Yeah. Yeah, to answer some of the questions in the chat, yeah, this problem is basically asking you to prove that no matter how the rooks are laid out, there are going to be 5 rooks that are not attacking each other.
Yep. So I like a lot of the ideas that you guys are putting through the chat and the Q&A. One thing I would suggest though is maybe trying to think about how we can apply Pigeonhole more than once in this scenario. It's not a big hint, but it may get you to the solution. So think about how we can place them, how we can essentially construct 5 rooks that don't attack each other, and how we can show that through Pigeonhole. And maybe I can add one more piece of advice. Remember that if 2 rooks don't attack each other, this means they're both not in the same row and not in the same column. So perhaps you can think about it like that. Yeah, again, I think I'll keep stressing. I think I said this was a small part, but I actually realized that this is actually probably a bigger part. Try and apply Pigeonhole more than once. So that's my hint. You'll have to apply Pigeonhole more than once in this scenario. Okay, yeah, so I think I'll get into the solution. A lot of you suggested something about diagonals, which is actually somewhat correct. So let's move into it. Michael, do you want to erase the drawing?
Yep.
Awesome, great. So what the overarching branch of this proof is that we're trying to construct 5 rooks who do not attack each other. So the whole idea is that these rooks none of these rooks will be in the same row or column. Okay, so we can say by the Pigeonhole principle, there exists a row on the chessboard such that there are at least 5 rooks in it. And so let's just make sure like why this is true. So we're essentially looking at rows. And so this is the whole idea that comes back to corollary 2, that if we take 41 and we divide it by 10, that's 4.1, and then take the ceiling, that's 5. And so there will at least be 1 row in the chessboard that contains at least 5 rooks in it. And so we'll call that row A. And so now let's think about it in some sense that we completely remove row A for the sake of argument. So now we have at least 31 rooks and 9 rows. And so I'll explain why we have 31 rooks, or at least 31 rooks. So notice that since this is a 10 by 10 chessboard, a row can have at most 10 rooks, right? So when we remove row A, we're kind of accounting for the worst case scenario, in the sense that there are 10 rooks in that row. And so if we remove row A, we'll be left with 31 rooks. And of course, when we remove one row from 10 rows, we get 9 rows. And so now this is the idea of applying pigeonhole principle again. Now we can show that by applying that same corollary 2, there will be at least one row that contains at least 4 rooks in it. And we will call that row B. Now we remove row B, and we say that there are at least 21 rooks in 8 rows. And so the same idea that we assume the worst case scenario for row B, we assume that there can be up to 10 rooks in that row. And so we will remove it for the sake of argument. And we apply pigeonhole principle again to these 21 rooks in 8 rows. So there exists a row C with at least 3 rooks. And now we remove row C again, and we have at least 11 rooks and 7 rows. So applying corollary 2 again, so one row contains at least 2 rooks. We will call this row D, and then we'll remove it again. And then we'll finally consider a last row with at least 1 rook, because we took away 10 rooks for the worst case scenario. And so it'll have at least 1 rook, and we'll call this row E. And so just a thing to make sure we understand here is that what we're considering as our pigeons and our holes, our pigeons are our rooks, and our holes are essentially the number of rows we have left, right? And so we're essentially showing that we can construct some rows with at least 5 rooks, at least 4 rooks, at least 3 rooks, at least 2 rooks, and at least 1 rook. And now this next slide is going to explain why that whole thing is useful. So after showing like what we showed in the last slide, we want to construct our 5 desired rooks. So we'll take a row. We'll choose any row. We'll choose any rook that we call R1 from row E, which we know exists because row E we showed has at least 1 rook. So this is essentially we'll take this, right? And this is just this diagram at the bottom is completely hypothetical. I'll show it at the end like why we can have many different forms. And so what we do next is we choose a rook R2 from row D, such that it does not attack rook R1. And so we know that this rook exists because there are at least 2 rooks in row D. And so if one of them is essentially in the same column as rook R1, we can essentially just choose the other one. And so that'll be our rook R2. And then from row C, which we showed has at least 3 rooks, we'll choose rook R3, such that it does not attack the 2 previous rooks we chose, R2 and R1. And again, notice that we can do this because we have at least 3 rooks in row C. So let's say in our worst case scenario, in row C, there exists a rook that is in the same column as R1 and a rook that's in the same column as R2, so it attacks both of those. But we have 3 rooks, so we can definitely find another rook in that row such that it does not attack R2 or R1, meaning it'll be in a different column than R2 and R1. And then we do the same thing from choosing a rook R4 in row B, such that it does not attack rooks R1, R2, and R3. And then we choose rook R5 in row A, such that it does not attack the previous 4 rooks. And you can see we essentially just created 5 rooks that don't attack each other in this scenario. And I'll explain really quickly like why this diagonal situation does not necessarily have to happen, but it can happen.
Yeah, so like in general, what we're doing here is just using pigeonhole, right, to guarantee that there are going to be more rooks than could possibly attack each other in each ascending row, right? And we'll be able to go over this more. If you guys have any questions, please make sure to fill out the feedback form that I linked in the chat. But yeah, thank you guys so much for attending this first session. Please visit our YouTube. Please subscribe to make sure that you guys are updated with the videos and whatnot. We're going to be emailing out the homework soon and the slides as well. And yeah, so if you guys thought that this material was perhaps a little bit too challenging, you're more than welcome to attend our session for 5 to 8, which is happening right now. If one of you guys could link that in the chat quickly, which is happening right now, so be sure to go check that out. But yeah, tonight, sure, if you have any time, just to check out our homework problems and fill out our feedback form with any questions you might have. So, that we can go over.
At the end of these presentations, we have 2 homework problems. So just check them out, put feedback or any questions in the forms that Michael sends out. And also for this, if you want a last homework problem, if you want to consider some sort of a different case for this problem, you can consider if we have 33 rooks placed in an 8x8 chessboard, and we have to show that there are 4 rooks that don't attack each other. So check that out if you'd like. And yeah, we hope to see you again tomorrow.
Thank you for coming.
Thank you for coming, guys.
All right. Thanks, everyone. All right.